You know current. In this lecture, you will know what causes current or how we can drive current. Well, it needs potential difference. A lot of people just don't know what is potential or what is its linkage with work done or how a potential difference creates a force or even what is the direction of the force created by that potential difference. It is along the potential energy dropping direction. Nobody will tell you all of this, I'm quite sure. Here, I'm going to give you crystal clear concepts and deep understanding. That done, we will get into electrical circuits where a battery is driving current. But most importantly, what exactly does a battery or cell do? Does it do any work? Well, someone has to do some work in order to deliver energy or power to an appliance like a bulb. Welcome to the portals of real learning. Don't skip and listen carefully right till the end. Before we go forward, I would just like to revisit some points of the previous session and just amplify on them, and also some points that missed out. So when we talked about this truck carrying an inflammable liquid and the truck having an iron chain that touches the ground, we said that it prevents sparks. It prevents sparks because any charge that builds up due to the friction of the tire with the road doesn't stay within the truck, it flows down to the earth because we are providing a path to it. So this chain is touching the ground and it is made of metal, which is a good conductor, which ensures that no charge remains on the truck and therefore no risk of a spark. That is one point. Second, talking of this atomic structure, one important point was there's a force between charges and like charges repel and unlike charges attract. And the force between two charges Q1, Q2 is written like this: some constant K into the charges multiplied by product of the charges divided by the square of the separation between them. That is the magnitude of the force, and this is also called Coulomb's law. Furthermore, like charges repel and unlike charges attract. So this electron is attracted to the proton. So that point must be highlighted. And finally, talking of resistivity and conductivity, we talked about both the things. A good conductor has a low resistivity and a bad conductor has a high resistivity. We also talk of another parameter quantity called conductivity. And conductivity is a reciprocal of resistivity. So we can say a good conductor has a low resistivity or a high conductivity or vice versa. All right, so we ended the session last time by asking this question: what makes charges flow? And we ended by saying that it flows due to a potential difference. And we likened it to the case of water flowing from high pressure zone to low pressure zone, water flowing due to a pressure difference, heat flowing due to a temperature difference, and charges flow due to a potential difference. Let's understand potential now. For that, let's take the example of gravity. If you have a mass at a height h and you drop it, you release it. It drops spontaneously downwards. Why does it fall? You would say that it is a weight, it is a force that is pulling it down. That is correct. But for forces like gravity, which are called conservative forces, we can associate a scalar function called the potential energy function, which pretty much describes the force, the magnitude, and direction. So instead of talking about forces, we can talk about potential energy function or potential function also. So we say that it must go, if it is free to move, it must go from a high potential zone to a low potential zone. We say that it had a certain potential energy here, mgh. When it drops and hits the ground, it gains kinetic energy at the expense of potential energy. The loss in potential energy is the gain in kinetic energy. But how did it get this potential energy? Somebody lifted it from the ground. That somebody, when the mass was here, that somebody exerted a force like this, which was just a little bit more than the weight, so that the mass didn't get any appreciable speed, therefore didn't get any appreciable kinetic energy. But this external force did work. The force was upwards, the displacement was upward, therefore it did positive work. And if it did positive work, this mass should have gained that much energy. So it has gained, but not in the form of kinetic, in the form of potential energy. So we say that the work done by the external agency is equal to the change delta U, change in the potential energy. We do take the surface of the earth has zero potential energy, then we can give the absolute value of potential energy to a body at this height h, which is mgh, because work done by the external force was force which was just a little bit more than mg into the height mgh. So if the initial potential energy is zero, then the work done by the external agency is simply the potential energy at that place. So what is potential then? First of all, potential energy, let us repeat this. It is the work done by an external agent in bringing a certain mass from zero potential energy point to this height h. And this work was mgh, and that is the potential energy. Given that surface of the earth is taken as zero potential energy. What is potential? Very simple. Potential energy per unit mass. That means work done per unit mass in bringing that unit mass from zero potential energy level to this particular height. How much is that? Work done mgh per unit mass. So mm cancels gh. Potential is a function of the height. Larger the height, larger the potential. And we can see that a body moves from, if it is free to move, it will move from a large height to a smaller height, not the reverse. It moves spontaneously from high potential to low potential zone. You don't have to do anything, just release it. But the reverse is not spontaneous. To move a mass from low potential to high potential, that means to raise the mass by a height, you have to do some work. That is not spontaneous. So potential energy and work done are all very closely related and closely related to the force as well. So a mass drops spontaneously because it loses potential in the process. Everybody will try to go to the lowest potential if free to move. A mass on the ground doesn't spontaneously move horizontally, because horizontally movement means what? Go from here to here. It must go from high potential to low potential. It will move due to a potential difference. But if it goes horizontally, there is no potential difference. It doesn't move. So we can therefore say that the force is along that direction, along which the potential energy reduces at the fastest rate also. If potential energy reduces, then the potential also reduces. So therefore, the force direction and the potential are closely linked. Force is along a direction which is high potential to low potential zone. So we can only talk in terms of potential difference because that also defines the force direction. So just to restate, the body gained potential energy when external force did work on it, and the work done by the external agent is the change in the potential energy of the body. Now let's take this concept to electrostatics and electricity and charges. Suppose there's a big fat charge plus Q sitting over here and it is fixed, it can't move. And we have a small test charge which is also positive kept at infinity. If it is at infinity, there's no force on it. Coulomb's law is what? Force between two charges is K Q1 Q2 by R square. If R is infinity, there's no force. We also take a convention that the potential energy of the system is taken to be zero. That zero definition is very important. In the case of gravity, the zero potential energy definition was surface of the earth. Here we take when the charges are at infinite separation, then the potential energy is taken to be zero. Now, if an external agency comes in like this and applies a force to move this charge ever so slowly to bring it closer and closer to this capital Q, then it is facing a repulsion. As soon as it comes a little bit closer, it faces a repulsion by the plus Q. It has to overcome that repulsion and push it, so it is doing a positive work. The external agency does positive work in bringing this charge from infinity to this point. Infinity means zero potential energy to this point. We can prove that the work done by this external agency is a constant, same constant here, K, Q1, Q2 divided by R. R is a separation. So this is the potential energy between two charges kept at a separation R. And that is also the work done by the external agency. Potential in this case now is potential energy per unit charge instead of per unit mass. So Q by R divided by the charge, that is divided by the Q, gives us KQ by R. So you have a charge capital Q. You talk of any point at a distance R, you have the potential there. Now look at this function, potential function. Let me write it once again, KQ by R. Smaller the R, larger the potential. So if I compare this point versus this point, you know, this is at a higher potential than this one. Smaller the R, larger the potential. If I place a charge at the high potential point, it will get repelled, right? The force is there, but we are not talking about the force. We are trying to talk in terms of potential. So it moves spontaneously from this place to this place. It spontaneously moves from high potential to low potential. So it is repelled to the right. The force on the Q is along that direction. Now, look at this expression. Larger this charge, larger the potential. Larger this capital Q, larger the potential at a distance R, and larger will be the force also. Now, suppose I give lot of charge to one guy plus positive charge to one guy plus Q1, and I give lot of negative charge to another guy, let's say minus Q2. Then the very process of adding charge to this body gives it a high potential. Larger the Q, larger the potential. We talked about the potential at a distance r from it. Here I'm talking about the potential of the body itself. That is not hard to relate. See, if I take a point very close to it from here, let us say, very close to this body, it has got a potential k times q by r, but then the question is, that time it was a point charge, this is not a point charge, and so on and so forth. But in general, we can say that it will have this format, kq by r format. And if I talk of the body itself, it will be proportional to the charge that it has got and inversely proportional to its dimensions, maybe the area, maybe the volume, maybe the radius, something like that. So anyway, the point to note is this gets a high potential. Lot of positive charge means high potential, lot of negative charge means low potential. Or even two bodies had positive charges only, one had more and the other had less. Then again, there's a potential difference between the two. Both of them are positive potential, but there is a potential difference between the two. If you place a charge in between, a positive charge in between, it experiences a force. You will say that, yeah, obviously, because it's getting repelled by this Q1 and attracted by this Q2, that is negative, so therefore the net force is to the right. Absolutely correct. But think in terms of potential. This is high potential, this is low potential. In this direction, the potential is reducing. The force on a positive charge is along that direction. So please note, guys, a positive charge will move from high potential to low potential, and that is spontaneous. And a negative charge will move from low potential to high potential. If you place a negative charge, it will flow like this because think of the force first. It will get attracted to the positive charge Q1 and repelled by the negative charge Q2. That is why it is going to move to the left, opposite direction. So this is very important. Positive charge moves from high potential to low potential, and negative charge moves from low potential to high. So, in order to make charges move, we need to create a potential difference. And that we can do by accumulating charges, plus charge here and minus charge here. And that is what a battery or a cell does. This is a very familiar dry cell. You know, this metallic cap is the positive terminal, the bottom surface is the negative terminal. And if you connect up a bulb across this, the current flows. Current flows means charges flow, and the positive charge moves spontaneously from the positive terminal to the negative terminal. So if you connect up a bulb like this now, it will glow because a current will flow. And current also is written as I. It is taken as the direction of the flow of positive charges. So how does this cell maintain the potential difference? That is due to chemical action. A cell is able to maintain a potential difference across its terminals by chemical action. This particular cell contains zinc in ammonium chloride. Your mobile phone battery is lithium ion. Your car battery is another technology which has lead plates dipped in sulfuric acid. It is all chemical action. It is all due to chemistry that we are able to accumulate charges plus and minus, thereby creating a potential difference, thereby creating a force on a charge that is free to move around. That is the concept of potential. Now, when you talk of electrical circuits, we have to hook it up something like this. Here what you see is a battery, and the symbol for a battery is two lines. The bigger line is the positive terminal and the smaller line is a negative terminal. That is a cell. Actually, we use cell and battery interchangeably, but strictly speaking, a battery is a group of cells. Okay, so we have this cell and a bulb, and we have a switch. This is called a plug switch. By pressing the plug here, the circuit is called closed. There must be a closed loop for the current to flow. Otherwise, the bulb will not glow. Moment you close the switch, then the bulb starts to glow. That means the current starts to flow like this through the bulb, then through the switch, etc. Now, this is called an ammeter, and that is a symbol for ammeter. That is an instrument which measures the amount of current that is flowing. So, the presence of this cell drives the charges. If this cell was not there, this current wouldn't flow. Thanks to this cell, we have a current flowing. And also, we need to have a closed loop for charge to keep on flowing. And one more thing, if the light is coming out from this bulb, that means the bulb is radiating light energy. From where is it getting that energy? The only person involved to give that energy is the battery. So when the current flows, the battery does work. There is no free lunch. Unless somebody does work, the bulb doesn't get the energy to then send it out as light energy. Somebody has to do work. So how does the battery do work? That is what you're going to discuss. This is a children's toy where, in order to keep the child occupied or interested in the whole thing, if a car is placed here due to the incline, it spontaneously goes down, down, like this and comes in here. But we want the child to be engaged. If the car stops, then he's going to cry. So somebody has to lift this car and place it back here. Once you place it, then you don't have to do anything because then the incline takes care of the rest. Why is it flowing spontaneously? Because of the incline, and it is going from high potential to low potential. But this car had to be lifted up. If the height difference was h and the mass was m, then the work done by person who's lifting it up is mgh. In this case, there's a battery operated device here, this green color thing, which has a platform. The car comes in here and this is rotating. So the platform now takes the car, lifts it up, and places it here. Every time the car is lifted, an amount of work mgh is done by this device. And then the car keep going round and round the circuit. In a current, we have charge going round and round the circuit repeatedly. So, the moment you close the switch, there is a positive terminal, negative terminal. Imagine a free positive charge. A free positive charge here would say, oh, now there's a path. It will spontaneously flow from high potential to low potential. And that constitutes current. All right, so it comes here. The positive charge has come here. It won't go from here to here spontaneously. Somebody has to lift it up. From low potential to high potential, the motion, the movement is not spontaneous. Somebody has to do the work to lift it. Just like in the case of this car, somebody had to lift the car and then place it on the top. Here, the battery is lifting the charge from low potential to high potential. Just lift it up and then the charge will move. Every time a charge comes here, the battery lifts it up and does the work. So, how much is the work done? Now, think about the concept of potential energy, etc., that we discussed. The work done was equal to the charge multiplied by the potential difference, delta V. Potential was a work done per unit charge, right? So if you take a charge and lift it up from, say, zero potential to a potential of 10 units, then that charge multiplied by the potential difference is the work done. And the unit of potential is volts. You hear the word voltage quite often. So a battery would have written on its body a label, say 1.5 volts. 1.5 volts is the potential difference between its positive and negative terminals. Every time a charge Q is lifted from negative to positive, an amount of work is done by the battery, that is that charge multiplied by 1.5. So how much energy is given to each coulomb of charge as it passes through a 6-volt battery? That is the charge 1 coulomb multiplied by the voltage difference through which it was moved, 6 joules. And by the way, in a metallic wire, it is only the electrons that flow. There are no free positive charges. So electrons flow like this. But we have a convention that we take the current direction as the flow of positive charges or opposite to the flow of electrons. So battery is very crucial to ensure that there is a current in the circuit, and every time a charge goes around the circuit, the battery does work. Now, you may not have a battery always. You may have an AC power source or some other power source. That power source is doing the work, and that is why all the appliances connected to that circuit, they get that energy. Maybe a light bulb, maybe a fan, maybe an air conditioner, whatever. They consume the energy. And who is giving that energy? That power source is giving that energy to them, right? So this was a very important discussion. We will proceed from here towards Ohm's law.